Do you hear me? Okay, thanks, Beth. Okay, I share the screen. I waited a little for other students. The noise is related to the fan of my laptop. If we wait, and as you hear, it is low, okay? Be used to it. Don't worry about it. I try to speak louder. The number of students for the first class is 36, but now the attendance is here 14. Yeah, Muhammad Rashid Mahdi. Yeah, basically fine. I don't know why, but it is related to my system. From the first day that I bought this laptop, this voice is with it. I used to it, and other students also used to this voice. They know that my laptop has this voice. I don't know. It is Sony. It is a Vaio. The brand is okay, but really I don't know why. Of course, it is better I show my laptop and to the expert. Maybe there are some problems, but really I don't know why. And finally, Naima comes to class. Okay, now it is okay? Another thing besides the sound of my fan is related to the speed of your net. For instance, sometimes some students said that my voice is not clear and it has some interrupts. It's also related to your internet speed. It is not related always to me. Okay. I wanted to record another video for the previous sessions, but I preferred start to a new topic, and then after that I will record the remain for your offline class. Okay. If you don't have any question, we start the teaching. Oh, okay, yeah. Just a moment. there are some words in this field. For instance, supervised learning, unsupervised learning, reinforcement learning, validation, cross-validation, training, batch, online system, offline learning system, and like this. We said something in the, we said cosine and sinus. Okay? And if you attention to this equation, you see that this periodic function, cosine and sinus, has some coefficients. And we can calculate these coefficients A0, AN, and BN. Okay? For instance, A0 for this function is like this. Can calculate by this equation. Okay? Like this. And I again remind you that I'm writing with a mouse. Then if my handwriting is not so good, it is because of this. Okay. And then after that, we said that all periodic functions don't have period 2 pi. Maybe the period duration was 2L. I mean, instead of 2 pi, maybe we have 2L with a generic periodic duration. In this way, again, we have some real representation of Fourier series. Besides, we can represent Fourier series in complex version like this. For instance, we said that f(x) is equal to sigma, like this, Cn, exponential function, and the power of this is I and px alone, but the periodic is here. And the coefficient Cn can calculate it from this. We have some properties in this field. For example, if our f(x) was real, then Cn or C minus n. If we have f(x) real, or for example even, you know even function, You know even function? If you know, please type it. What is the even function? Nobody knows? Nobody. Okay, I explain. Function, I forgot this function like this. This function is an even function. The symmetry of this function is related to the vertical line. And if you see f minus x is equal to f(x), we call this function f(even). Okay? In contrast to this function, we have f(odd). f(odd), the shape of f(odd) is like here. I write it here. The symmetry of odd function is related to the central points to 0. And if you remember, f minus x is equal to minus f(x). Then this function is odd and is even. Okay? Okay. Anyway, if our function was real and even, and what is the real? Real means the function doesn't have imaginary part. All the things, all the measurements in this f(x) is real. Doesn't have any imaginary parts. Okay? And if our function was real and even, then our Fourier series coefficients is again real and even. Real and even, we can write like this. For EVs, for real, we can say that the conjugate of Cn is equal to itself. And if our function was real and odd, okay, the Cn would be completely imaginary. The Cn is completely imaginary, purely imaginary, and also even odd. It means like this. Okay? Do you have any questions? No question? Okay. Okay. We know these things. I hope you to know these things. After that, we said that, okay, our functions aren't always periodic. We have some functions that they aren't periodic, for instance, like this. It is not periodic. And how can analyze this type of functions using Fourier analysis. Because of this type, Fourier means that we transform a function from X environment, from time environment, okay, to another environment, to another space. And another space is Fourier space, is Fourier environment. If we call it fx, okay, f is dependent on x, and if we transform the function to the Fourier space, the function is related to omega, to frequency. And why we use Fourier transform? What is the advantages of Fourier transform? Because sometimes in image processing, in signal processing, the information of frequency is better represented, is better presented in Fourier space. Okay? Some information, then in summary, some information in Fourier space is better represented. Okay? Then we use these for equations for transforming this function to the Fourier transform. And after that, some person who names Curie and Touquet developed this commonly Fourier transform, and they introduced fast Fourier transform, and this type also has some advantages. We try to see the advantages in the next slide. But before it, we introduce the application, one application of fast Fourier transform. Please imagine it in a cylinder here, okay? This cylinder sends, for instance, electromagnetic waves and try to detect a target. For instance, try to detect this airplane. It sends electromagnetic to target, and the target reflects the waves. Also, the target observe a few part of waves, and from the reflection of this target and receiving it, this object can understand the place of this target, or can understand this target, can track this target. But it is too ideal in the real world. We have clothes, we have trees, okay, we have trees, we have other targets around it. We have some instruments in the space that they also may reflect the electromagnetic waves. Then the received waves here is not related only to this target. It is clearly that related to other things like this. Then we then we receive electromagnetic waves with noise here. Okay? And from this system, from this simple system, we can use or set other example. For example, stealth technology or radar jamming system. Sometimes, attention to this. The above images. These objects the radar send waves, but the shape of target is specific, and the reflection waves doesn't go to the sender. The target reflects waves to other directions, as you see here. Or maybe the materials of target was special. Then instead of reflection, the material observed all the waves. Then we cannot track the target in this way or in this way. Okay? And another thing in this field is a jamming system. For instance, you imagine this target and imagine this airplane or desired object. The radar sends waves, but another fake target, another fake airplane send waves to radar. And then in this way we confused what is the desired object, what is the main object here, one or two. How we can distinguish between one or two targets, target one or target. Then we called it parasite. Okay. Then in both system, in both example, we can use Fourier transform. How? In the next slide you see it. You don't have any questions? Yes, surely I uploaded it. Okay. Today I uploaded. Okay, another question. Yasmin Nazim said no sound, but I think it is okay. Maybe it is related to your internet. Okay. Please imagine we have a noise like this. We have a signal with white noise like this here. Okay. We want to distinguish and this noisy signal received in the by radar system, okay, without any noise. Then we filter the noise. We want to filter the noise. If we use the Gaussian filter like this, with bandwidth for example, if we go in the Fourier space by the filter, then the outcome, the result is like this. And then if we in original signal, we see that the pink and blue is not as same as but they are near to each other, and it is acceptable for us. And on the other hand, in the right figures, if we select our Gaussian filter with wrong parameters. For example, we again use this Gaussian filter. The bandwidth is 0.2, but it's centered 15 frequency. Application in domain, we have these, and then if we use full term, this blue now, okay, and it is clear that this filtering in the Fourier domain, we can remove the application of a Fourier transform is denoising the signal. Is denoising the signal. How? For example, like this. Example. Don't question signal in Fourier domain. So in A, it is the one signal. B is the average of two signal in Fourier domain. C is the 5, average of 5. Signal, and D is the average of 100 signal in Fourier. It is clear. It is clear that large number of signals, and we average them, result is better. Do you think why? It is related to the noise, the kind of and the type of noise. Because here, the noise is white. the center of noise, the frequency of noise is 0. Then, by averaging in frequency domain, we can remove the noise. It is another advantages or another application in this field. But in contrast to this example in the left, consider this figure, right upper. We have many signals in time, and the shape of this. We have noise for each signal in time domain, and if we use Fourier transform, we have this figure. You see, in the Fourier transform, the location of noise missed. All the Fourier transform of these above signals has the same, you see, noise signal in Fourier domain. And we cannot distinguish between, for example, 1 and 2. If we use Fourier transform inverse, really only with this information we cannot relate 1 or 2 to this signal or this signal or another signal. This is the disadvantages of Fourier transform. The Fourier transform cannot distinguish the location of some frequency. Okay, and this is another application of fast Fourier transform. The above figure shows that the average in the time domain, and the lower one is the average of signals in a Fourier domain. It is clear that the averaging in Fourier is better than the time domain. In time domain, the information lost, the information missed. But in Fourier domain, in frequency domain, the noise, after averaging, the noise can be observable, can be detectable. Okay? The code of this and the explanation of these things is chapter 13. Completely, the codes step by step explain and achieve this diagram that I explained to you. Okay? Okay. And in summary, we can say, for instance, consider this signal ST. It is in the time domain, and if we use Fourier transform, we have this diagram, this figure. Totally, for example, if I zoom on it, if you consider this figure and attention to the changes, time changes. Time changes can be reflected by frequency. Time changes can be reflected by frequency. I mean, for example, imagine this signal and imagine this signal. Both of them in time. Finally, one student type something. Please let me read it. Okay, I explain. Okay, consider these two signals. What do you think about the frequency? The frequency, we call the frequency of the above signal F1, the frequency of the lower signal F2. Which of them is higher, F1 or F2? Please type it. Please type your idea about the frequency of these two signals. The frequency of above signal or lower. Thanks. Mr. Ali Abdul Abbas Hussainam Jamali, if I pronounced correctly, said that the second. Yeah, it is correct. Frequency means changes. I will answer you, Safa Abdul Jalil Tarwil. I will explain. Please wait. Okay. Then we have changes like this. Now the signal is lie on this pink. Besides, we have changes here. If we called it F1, F1 of these changes here in this part is greater, for instance, F2, we called it A, we called it B. F1 is higher than F2 in part B, because the changes of signal in A is higher than the changes of signal in B. Okay? But if we use Fourier transform, we only said that, okay, we have some frequency around 0 here. Maybe this is related to this pink. We have this frequency F1, maybe it is related here. I wanted to say that by using Fourier transform, we can access only the amount of frequency. But we cannot say, okay, F1 in the first of the signal. We cannot see the location of F1. By Fourier transform, we can access to the frequency context of the signal. Okay? Only we can access to the frequency signals. And then, this is disadvantages of Fourier transform. And another question is that what is the Fourier transform good for in the context of signal processing? If Fourier transform has these disadvantages, then what is the benefit of using Fourier transform? Why we use Fourier transform? To answer this question, please consider two signals in left and right. As you see in right, we have some changes in signal, but these changes repeated. After duration time is repeated. Okay? And consider the left signal. We have some changes here. Then the change here is higher. Then again higher than the previous parts. Okay? The frequency content, the frequency information in the left changes during time. The frequency information changes during time. But in right, the frequency context, the frequency changes are stable during time and repeated again by again. Then, by our knowledge till now, we said that the Fourier transform is good for this type of signal, but it is not good for the left. Because for left, we only can say, okay, we have 15, 100, and 150 frequency. And we cannot say the location of it. And again, please consider the right Fourier transform of signal. Again, we see that, okay, 50, 100, and 150. These two Fourier transforms are similar to each other. We call the right signals stationary signal. It means a signal with frequency content unchanged in time. Or another way, all frequency component exists at all times. But in the left we have non-stationary signal. Frequency changes in time. And ultimately the Fourier transform is superb for one thing, characterizing a stationary or periodic signal. Because they are unchanged during time, but it is not proper for non-stationary signal. Our bio system, if we have some biosignals, for example, the signals of heart, or human heart, we called it ECG. The electrical signal of head, we called it EEG. They are non-stationary signal. Then we need some other methods for this non-stationary, for analyzing of this non-stationary signal. Okay. If you don't have any question, we stop till slide 11, and the remain was for offline that I will record it and upload it in the LMS. And one student said that Muhammad Rashid asked many questions. No, this is related for advanced algorithm. But in DSP, I also teach DSP. In DSP, we have discrete Fourier transform. And discrete Fourier transform is a little different from this. The formulation, the concept is different. But for the introduction of Fourier transform, they are common for both of them, DSP and advanced algorithm. Oh, okay. It is good recommendation. Yes. He said that we uploaded the PDF before the session. Okay, why not? I will do it in the next session. And Safa Abdul Jalil will ask, we depend on the book or slides, both of them. The PowerPoint, the slides, is the abstract of book. Then you please first see the slides and see what is the important things, what is the important context. And then after that, you can study in details by book. Okay. For instance, we review all of these and we abstracted, we shorted all these in only 10 slides. Okay. Any other questions? Okay. If you don't have any question, we finish this session. Thanks for your attention. Thanks for your attending this class. And I hope to be fine and have good time. Be successful. And I said goodbye for all of you.